Okay, after a long 3 or 4 hard days of work, I think I've got something that I'm happy with. First thing I want to show you is as before, we have a schematic and a PC board, but you can actually attach other files to your project, which provides good locked-in documentation for, say, the chips you're using, and it loads them up in your PDF viewer when you select them later. So here we've got the MCU, we've got the CANBus driver, we've got the USB driver chip, and the current sensor chip itself. So that's very handy. So now let's jump over to the schematic. Here we go. This is the whole deal. And I could not have built this without a lot of help. So many Google searches, so many stealing things from other people's circuit board designs, and it's just crazy. So let me walk you through the subsections. This is the whole thing, and I'm working on a 16-inch screen on a laptop, and I wish I had more pixels and more physical area because I'm having to zoom and pan around all the time. But this is the whole thing. This is our screw terminal with 12 volts and CANBus. This is the power supply with a lot of filtering and LEDs to show things are working. This is the CANBus transceiver with LEDs to show things are working. This is the micro USB connector with the USB driver chip with lots of filtering and LEDs. This is the MCU with surprisingly few inputs. There's some power supply inputs with lots of filtering. We've got CANBus in and out pins. We have USB in and out pins. We have the current sensor, which is the heart of the thing, with one analog input. And we've got the debug header and some more power supply. And we can zoom in and see some of this stuff in more detail. And I'm working with a 32-pin MCU, but the crazy thing is it's got so many things that are built inside of the functionality of the chip, but everything is multiplexed. The pins are multiplexed to multiple things that they can be. I remember back in the good old days when pin 7 was analog input 2. No, everything is so abstract that you've got to just wire things up, and then you go in with the software and you tell it what you want the physical pin mapped to in the logical functionality. So I'm only hoping that I've got the pins wired up correctly. That helps us get to where we want to be. All right, now I did the forward design changes 100, 300, 500 times, which reflects the circuit onto the circuit board, dropping components, adding wires, deleting wires. So let's pop over and take a look at how the circuit board ended up. And here we go. You can see things are a little busy because I've got a bajillion errors that it's detected when I was trying to check the design rules, but I found the solution. Tools, design rule check, delete errors. It's right here. After you run the design check, you can get rid of all the errors on the screen. And here we have clean board layout. Now I've hand laid out to the 1/4 of a millimeter every single component on the board. I hand laid out every trace. I gave up on the auto router. This is a weird board. There's a lot of power. Everything's surface mount. And it's got the crazy current sensor with its crazy pads and my crazy screw terminals. So I just figured I would give up on the auto router and do my thing. Now, the cool thing is each of these layers is selectable. So we can turn everything off. And so all we have left is a board outline. And I don't know why this little bullseye symbol is here. But if we look at the documentation on the top, basically each component draws this blue line to show the maximum physical space that the component's going to take out. But if we overlay the sill screen on that, we can see that some of the components are actually physically smaller because they have pins that extend outside the size of the documentation. So the blue lines are good to make sure you're not overlapping anything with your spacing. But for now, let's get rid of that. And we're going to draw in the top copper layer. And this is the layer that faces us on the board. When I was laying out circuit boards, I was told, think of when you're putting grass on your front yard, green side up, and bottom copper is red side down. It wasn't brown, so we went with red back in the good old days. But you can see this is pretty much exactly how the board's going to get laid out. I did the vast majority of the layout on the top in green and a little bit with red on the bottom, mostly for power and ground, but a couple of signal traces that I just couldn't get to where it needed to go, primarily because I'm using surface mount technology components. You have no access to these chips on the bottom of the board, so sometimes I had to come out, pop through, and then go to where it needs to go. Okay, so a lot of the circuit board parts are laid out nicely. I'm going to zoom in. You can see this is the MCU. I'm just running straight through at the pins. Luckily, this is ground. That comes through nicely. But then we can also look at some other common components like this LED and this resistor. LEDs are always paired with a resistor to limit current. This is an inductor to make nicer power going into the MCU. This is our debug header with the pin header that looks like this. You can see the gold wires make a right angle turn as they come out, and they'll get soldered down onto that pad. We have this reset switch, which I couldn't find an exact match to the component that I ordered off AliExpress, so I just did my best guess as to where the pins are, the pin spacing, and how the pins are actually connected. I may have to do a little surgery on the board to get that to lay out properly. And you can see the power and ground lines are much thicker than the rest of the signal traces. You always want the traces to be as big as possible for power and ground. And the program's pretty nice. When you, in the schematic, when you mark a trace as belonging to the power or ground family, and you go and you click a trace, it will always use the power width setting. Now you can select it and change to size. You can select power minimum or power nominal. We are at power nominal now. If we go power minimum, it shrinks it down to a little bit smaller. But I've tried to leave all my power as the nominal size. This one here is signal minimum or signal nominal. Signal nominal and signal minimal are pretty similar. Oh no, that's actually much smaller. I've never used that. I've always gone signal nominal. I suppose if I was really pushing my design limits and the circuit board manufacturing company allowed something that small, I could get away with it. Position the connectors where they needed to go. The micro USBs right on the edge. The power connector is offset from the board a little bit, and the terminals are labeled. Now over here you can see this is where the current sensor gets soldered in, and it goes through this little routed hole. I had to create a pin mount for my mounting screw down terminal. I had to create a package and a schematic symbol for this. So I dropped those in, and then I tried to do the copper pour function, which looks like it should do the job, but when it did the pour, it basically poured copper, but it didn't connect these pins to this pin, even though there was a trace in the schematic. Right here you can see net number 0017. It didn't connect them together, so basically I poured copper on the front and the back and dropped about 1,000 via holes, which are plated right through the board. So the design rule does not like this, but it's pretty happy with everything else. I'm happy with the physical layout. Now, let's take a look at the circuit board that this thing thinks it's going to be producing. Okay, and to do that, we pop over to 3D view, and there it is. Now you can see a couple of interesting things right away. Not all of the symbols are photographically realistic. It draws just a red box on a lot of things. It would be nice if it was better, but it's probably a lot more has to go in developing the component editor to maybe able to drop in an image of what the part actually looks like and have it scale it nicely. But you can get an idea of at least where the copper traces are. You can look at your labeling. I've added labels. Obviously, I've moved around a lot of the component names so they'd be more viewable. I labeled things like here we've got USB receive and transmit LEDs, plus 5 volts OK, plus 12 volts OK, can transmit, can receive, this reset button, and I'm pretty happy with it. And we can also, now notice it doesn't show the VIA holes, it just shows it as solid copper, but on the bottom it does show the VIA holes, and I'm good with that. You can see how little copper I actually used on the bottom. These are just where it was impossible to run a signal, and the rest of it's power and ground. So let's actually go ahead and produce the files that are needed by my printed circuit board manufacturing company of choice. Okay, I've chosen this company JLC PCB because they've got really good pricing. They don't have a minimum order. Well, I mean, they give really good prices on 10 pieces, and I want 10 pieces. But they also don't have minimum board sizes, or the maximum board size is huge. So I'm happy with that. It's also a sponsor for a YouTube channel that I watch called Great Scott. And he does really good things, and I want to support him because this company seems to do good things. So what we're going to do is I've created an account and logged in, and we're going to ask for a quote on a 2-layer board. They're $2 for 10 pieces, as long as it's less than 10 by 10 centimeters. So that's fine with me. If the board was bigger, it would be more expensive, but I'm happy with that. So let's find out what they need to actually produce my board. So here, we want a PC board. We don't care about the stainless steel stencil, so we don't need that. So add your Gerber file. So we're going to need to put out Gerber files accepted in zip or RAR format. So we need to go back and produce a Gerber file in zip format. But let's take a look at the other things. We want 2 layers, and we need to know what our dimensions are, so we'll get that from the board. We want 10, standard 1.6 thickness for the board, green plastic. This is fine. Good standard copper weight, no gold fingers, standard FR4 material plastic and fiberglass. The panelization is fine, and there's going to be one design on the board. For example, we're going to do one design, and they work with larger pieces of fiberglass, so we're only going to put one on there, so that's fine. So let's go back and produce our Gerber file. Okay, in the meantime between edits, I realized I need to put a label on this thing. And since I'm going to be able to put different rated current sensors in here, I'm leaving a little blank where I can write in the maximum capacity of the board. Okay, so let's jump in and produce our files for the circuit board company. First thing we need to do is click on the board outline. You see the word board show up. We click on that, and we are 80 by 50 millimeters, so we need to remember that. Also remember, we do have a board. This is important. So we're going to go Output, Manufacturing Plots. Okay, you can see there are a lot of different things that you can send to the PC manufacturing company. Some of them we need, some of them we don't. So let's just quickly go through. Top documentation is those maximum size boxes for the components. We don't really need that, but what I've found is both DesignSpark and the PC board company need this thing called board outline turned on. So we're going to click and say yes, and we're going to put that in the top documentation layer. Top silkscreen we definitely need because that's got all of our part identifiers and labels for connectors. Again, I'm going to turn on board outline again just because I've run into problems with this. And this is not preserved between runs of the plot, so you have to go in and set this by hand each time. Top copper we need because that's where the electrons flow. Top copper paste we don't need because we're not having the board, the full product manufactured in a factory where they need to know where to put the solder paste. We do need the top solder mask because that controls where the solder goes when I'm building the board. We need bottom copper for those electrons. We do not need the bottom copper paste layer, but we do need the bottom solder mask. That's important because I'll be soldering through holes like the connectors for the in and the output wire, the current sensor, the 4-pin connector for power and CANBus. And we will be sending drill data. That's important. They need to know where to drill the holes. So let's go ahead and click Run. All right, let's take a look at the files that it output. So we've got Gerber files for bottom copper, bottom solder mask. I didn't ask for that. 3 drill files, top copper, documentation, top silkscreen, top solder mask, and the plot report. So let's make our zip file of the files that are actually needed by the company. We don't need the mop file, we don't need the report, but we're going to take all the Gerber files and the drill files except, oh yeah, solder mask, yes, I do need that. I thought it was the one about solder flow. So we've got bottom copper, bottom solder mask, drill, 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 top copper, top solder mask, silkscreen, documentation. So that's good. So we're going to go in here with 7-zip and create a file called DC current sensor CANBus .zip, normal zip parameters, okay. And there's our zip file. So let's upload this and see what happens. Okay, we're back at JLC PCB and we want our 2-layer board. So you have to click quote now rather than order now, but that's okay. So let's add our Gerber file, which is our zip file that we created over here. And it's going to upload it. And then we'll just confirm our board dimensions and look at the report that it generates. Okay, so it detected a 2-layer board, 50 by 80, perfect. We finished processing. So we've got 2-layer board, it updated that. I want 10 boards, standard thickness, standard color, standard finish, standard copper, no gold, standard materials. We're paneling, no, I'll do that. That's all good. And if we look at the Gerber viewer, this actually shows the analysis that it's performing for us. So there's the top board, which all looks good. Lots of pads, our solder mask looks good, our documentation layer looks good, and all of our design on the silkscreen looks good. Let's look at the bottom of the board. Everything looks fine. This is kind of unnecessary, but that's all right. And the analysis. The analysis all looks good. Everything's got a check mark, but we've got Gerber file with board outline and non-critical Gerber file. So let's go ahead and go back and we'll say save to cart. It's going to take 2 days and it's going to cost $2. And there we have it. There's our board. Wow. Instead of costing $5 for 10 boards, it's only going to cost me $2. I cannot believe how cheap this is. This company says they do 8,000 boards a day, 8,000 different circuit boards of whatever quantity selected. So I'm going to go ahead and check out. I'm not going to show you all my credit card information, but I'll let you know how the rest of the ordering process went in a moment. As you can see, the order went through. It's in a reviewing status. I haven't received an email acknowledgement from them in the last 10 minutes or so, but I expect that will be on its way. I'm in the shipping. You can see I have two choices: regular airmail for $5.55, which is reasonable. Shipping a package from China, I'm happy with that. Or DHL at $18.66. Not only is that more than what I'm ordering, but there's a big problem with DHL and UPS and FedEx receiving packages into Thailand. One, they send everything through customs, which not only slows you down, but you're forced to pay a really exorbitant incoming tax and duty on the product, which is totally out of scale with what the value of the product is. And at least my recent experience with UPS is they add on an additional what they call it, a disbursement fee that you have to pay, or they don't give you your box, which I think is a complete rip-off of their customer. And I don't want to go into too much detail. I'll probably have a whole rant video on UPS in Thailand. But just to wrap this up, the circuit board design is in China. It'll be made in 2 days and sent back to me, which makes me a happy boy. So the parts I ordered about a week ago are slowly trickling in, and next video will be me assembling this, hopefully for success. Probably version 1.1, because you know how these things go. So, see you soon. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.